In this video, let's create a linear regression model without using SkLearn library. We will be creating the linear regression using gradient descent method. In my previous video, I have explained the math intuition of gradient descent. Now let's implement it. Before that, let me quickly explain what gradient descent is and how it actually works. So in the gradient descent, we will be plotting the cost function values in the y-axis and the slope values in the x-axis. So we will be getting a graph like this. From this graph, we have to find the global minima value. The global minima value is a value at which the value of the cost function is minimum at a particular slope value. This value is where the error is minimum. The error means that the distance between the best fit line and the actual data points are minimum. So the value of the cost function is defined by the formula 1 by n sigma I equal to 1 to n y minus y hat the whole square. Here n is the number of data points, y is the actual value, and y hat is the predicted value. From this equation, we will be able to get the cost function values. In order to achieve the slope values, we will be using another theorem called as convergence theorem. In order to achieve the global minima, we will be using convergence theorem. The convergence theorem is given by slope value is equal to slope minus derivative of slope with respect to cost function. That means we have to find the derivative of the slope for the particular cost function. It is given by derivative of the cost function with respect to slope multiplied by learning rate. This is the convergence theorem. So what convergence theorem says that if the slope is high, then we have to reduce the value of the slope in order to achieve the minimum cost function. If the slope is low, it is vice versa. So we will be trying to reach the global minima value either way. If it is high, we are going to reduce it using convergence theorem, and we are going to increase it if it is less. So we will be implementing both the gradient descent and the convergence theorem together manually in this video without using any libraries. In simple words, we are going to find the slope value at which the error is minimum, and we are going to draw a best fit line with the slope that is obtained from here and the intercept. In simple words, we are going to get the slope value from this gradient descent where the cost function is minimum using gradient descent and this convergence theorem. Here I will be using experience salary data set for our model. Here I have imported the necessary libraries and I have read the data set using Pandas, and I have done some operations so that our data set is ready. Here we can see our data set that has experience in months and salaries in thousands. And I'm going to assign all the records of experience to variable X and all the records in salary to variable Y. I will be using ilog for this. Ilog is a function that is defined in Pandas that helps us to select a specific row or column from the data set. Here, ilog can be easily retrieve any particular value from a row or column using index values alone. So here I will be getting all the record. The semicolon with no values means select every record from the first column. It is 0 indexed, so 0 implies the first column, that is experience. And I will be getting all the salary records using this ilog for and I'll be assigning all the salary values to y using this statement, and the number one implies select all the column values from the second column. So and after that I'll be using SkLearn's train test split to split the data from these two variables that I assigned previously, and the test size here I gave is 20%. Then I'm standardizing the X-train data, and now we are going to add the bias term to our X-train value. So bias term is nothing but the intercept of the line. So in the line y equal to mx plus c is the intercept, and that intercept we are going to add it as a bias to this feature. So we will be using np.c underscore. What this np.c underscore is that it concatenates, it adds particular records of values to a feature. So we will be adding one here. In linear regression, it is an important step to add bias terms before creating any model. So here we will be adding the bias term to the standardized X-train values. So this np.c underscore, this particular function adds 1 to every feature. So this np.c underscore add 1. Usually 1 is given as a default value for usually 1 is given for every machine learning model as a default value. It is completely based on trial and error method. If we can study the features using feature engineering and assume that our intercept value lies above a certain value, then we can change the intercept value to be nearer to that value. Here by default we are giving 1. So this np.c underscore converts this 1D array. We had the extrain data as a 1D array. Now we are converting it into a matrix. That is, it is a two-dimensional array where every feature in the extrain contain one more value, that is 1. So that here we can see the values after adding the bias term. So in the equation that we are going to generate for the best fit line is y equal to mx plus c. So we have the x values here and we are adding the intercept value here. Now our extrain data has the two values, that is y equal to mx plus c. It has x values and the c values. So now let's continue to implement the gradient descent. Initially we don't know the values of the slope and the intercept. So we are assigning the slope value as 0 and the intercept value as 0. And then we are assigning the values for the hyperparameters. Here I am giving the learning rate as 0.01. So learning rate is responsible for maintaining the steps so that the gradient descent graph reduces gradually or increases gradually based on the slope value. If the learning rate is too high, the slope might jump extremely and it might never reach the global minimum. So it is necessary to keep the learning rate as much as low so that the slope gets down gradually and reaches the global minima. If the learning rate is high, it might never reach the global minima. And epochs is the number of times our model gets trained for the training data set. I gave 1500 as epoch so that our model gets trained 1500 times for here our model gets trained for 1500 times for all extrained data. And here I am getting the number of records for our data and I am creating two arrays such as cost and slopes to record the values of the cost and slope for each iterations. For each epoch, I am going to note down the value of cost and slope. So here I am giving a for loop. So here we are going to implement the gradient descent at a simple for loop. So here I am given the epochs in range. So this for loop runs for 1500 times. Now we are going to get the predicted values. For that we are going to multiply the extrain values with our slope and intercept value that we gave manually. So this line means that we are going to multiply this particular feature with our slope and the intercept values that we gave manually. So we are going to do matrix multiplication here. So we are going to multiply this with our slope and intercept. So the equation of the best fit line that we are going to generate will be y equal to mx plus c. So here we have the values 1, 0.625. We are going to multiply this with 0 and 0. This is the intercept value that we gave manually and this is the slope value. And here in this is the feature that we had in extrain. So this states that this is the intercept and this is the value of x. So what we are going to do is we are going to find the y value here. The y value is actually the predicted value that we are going to find. So in this case, we will be multiplying 1 with 0. This is matrix multiplication. We will be multiplying this row with this column. So we will be multiplying 1 with 0 and add it with 0.625 into 0. This will be 0 plus 0 and the entire value of y here will be 0. Hence we got the predicted value as 0. So here we will be doing this for every epoch. For 1500 epoch. So every time the value of the extrain and the intercept and the slope values will change. So now we are going to use the convergence theorem here. So if you wonder how we got this equation from the convergence theorem. So now we are going to find the partial derivative values of the slope and the intercept from the convergence theorem. This particular equation is derived from the convergence theorem. What convergence theorem says that we have to multiply the derivative of the slope with respect to the cost function multiplied by the learning rate. So convergence theorem states that slope is equal to slope minus slope minus derivative of slope with respect to j. M minus derivative of the cost function with respect to the slope multiplied by the learning rate. So this learning rate we defined as 0.01, and we are going to find the derivative value in this particular line. So this line is derived from here. Here j is defined as the cost function. So we are going to derive cost function with respect to m. So it is given by 1 by n summation of I equal to 1 to n y minus y cap the y minus y cap the whole square. So now we have to derive this equation with respect to m. So this y cap is y equal to mx plus c. So for the ith record, the equation will become like this: 1 by n sigma I equal to 1 to n yi minus mxi plus c the whole square. So now we are going to derive this equation with respect to m. So in the next step the equation will be like this: 2 by n into sigma I equal to 1 to n yi minus mxi plus c into minus xi. I have brought the power to the front and reduced it by 1, and I am differentiating this where m becomes 1, and I am multiplying it with remaining xi. So this particular equation will become minus 2 by n sigma I equal to 1 to n yi minus yi cap. So this is the predicted value. So this becomes y cap the whole square. This minus will be brought to the front. Actually this is not square. I brought the minus to the front, and the remaining xi will be there. So we are multiplying the data point with this predicted value. So this particular equation is given here. And if we derive with respect to c there for the intercept, we will not be multiplying it with the x value. As c is a constant, while differentiating it, it won't affect the equation. So we brought the two equations regarding derivative with the slope and derivative with the intercept. Now we are going to update the slope and the intercept value for each iteration. So we are updating the slope value. So we are updating the slope value with respect to the learning rate and the derivative. This particular line implies the exact convergence theorem. In this step, we found only the derivative of the slope and intercept, and now we are using convergence theorem for the slope and intercept. So now we found the slope and the intercept value. We will be able to form a line with this particular slope and the intercept. From the equation y equal to mx plus c, we will be able to draw a best fit line with the particular slope and the particular intercept. From that, we will be able to find the cost function. So we are using the cost function equation here, that is 1 by 2n into summation of y predicted minus actual value the whole squared here. And now we are updating the cost to the array that we declared. So I am appending the cost for this particular iteration to the cost array, and I'm also appending the slope array with the slope values. So by this we will be able to note the cost for a particular slope, such that when we arrive the global minimum, we will be able to record the particular values of the cost and the slope. And this slope will be responsible for the minimum error that our best fit line is going to generate. So now I am training this model. So the model got trained. Now we are going to visualize the gradient descent graph. So here we are able to visualize the gradient descent graph here. So the graph gets the global minima point near here. So our cost function value will be very minimum around when the slope value is near 7. So let's visualize the best fit line when we have generated the global minima. That particular value will be noted here, and now we are going to generate the visualization for the best fit line. So here we are able to see this is the best fit line with a particular slope. It passes in the middle of most of the data points, such that it is having the best slope and the intercept. So now let's visualize the global minima value and the slope and the intercept value. So we got the slope value around 7.26 as we visualized here. The slope value is near 7 and the exact value we got is 7.26 and we got the intercept as 26.61 and this is the global minima value. This particular value is where the cost function is minimum. So when the slope is 7.26, the error is minimum. So we got the cost function value as 13.27. Beyond this, the cost function will not reduce and it might tend to increase. If you want more accuracy or more selective value for the slope and the intercept, you can play along the learning rate and the epochs. If your graph doesn't look like a parabola or it doesn't have a curve, then you might change this learning rate. If the number of epochs is increased, the model gets more trained to the training data set such that it gets used to it and it might generate a better results. Learning rate should be an optimal value. If it is very less, the gradient descent graph will be very steep, and if it is very high, it will be in a horizontal manner. It might never reach the global minima. So deciding the learning rate value is trial and error. Initially you can start with this value, but eventually if you don't get any specific curve or global minima, you can change these hyperparameters and train your model furthermore, and you can get a optimal result. So now let's look at the accuracy of this model using the mean squared error and r squared value. So I'm getting a mean squared error of 26.54 and I'm getting an accuracy of 66%. So when I used SkLearn, I was able to get around 0.61. So it got 61% of accuracy when I used SkLearn, and it increased when I implemented it manually. Implementing is easy when using SkLearn, but it is important to understand how linear regression works in the background. So if we implement it manually, we will get a better understanding of how linear regression actually works and how gradient descent works. So this is all for this video. So we'll see you in the next video.